All right, welcome back to another notes video. So we're going to take a look at correlation today. So last video we talked about scatter plots and looking at sort of two variables and describing those relationships. And we were kind of limited to saying like, oh, it was a strong relationship, or it was a weak relationship, or it was kind of strong. Now we're going to be able to put some more exact values on that because we're going to deal with the correlation coefficients. So a correlation is a measure of the direction, so positive or negative, and strength of the, and I'm going to put this next word in all caps because it's key, linear relationship between two quantitative variables. All right. So the key there is that the relationship has to be linear. If it's not linear, the correlation coefficient is meaningless. So if you have a curved relationship or an exponential relationship or something like that, you really shouldn't be using the correlation coefficient. It's only valid as a measurement of linear relationships. So it's always going to be important that we first look at the graph before we calculate a correlation coefficient, because if the graph doesn't show a linear relationship, we're totally wasting our time calculating the correlation coefficient in the first place. So just a couple of things that you may have seen before, but it's always a good idea to remind you. Generally, the correlation coefficient, we're going to express that as R. So that is the variable we assign to the correlation coefficient. R can range from a minimum value of -1 to a maximum value of +1. All right, so you can never have a correlation coefficient that goes outside of this range. If you do, it means you made a mistake somewhere. So it's limited from -1 to +1. The positive and the negative represents the direction. So a positive correlation coefficient means that you have a positive relationship, or the points are kind of moving in a positive slope direction. As one increases, the other increases. And if your correlation coefficient is negative, then you have a negative relationship, which means as one increases, the other is decreasing. And an R close to -1 or to +1 is a strong linear relationship. All right, so as it gets closer to either of these values, the relationship gets stronger. And as it gets closer to 0, the relationship gets weaker. All right, and I would generally refer to correlation coefficients in terms of strength versus weakness. So I would avoid saying that the correlation coefficient goes up or down. All right, those are dangerous words to use. And the reason they're dangerous words to use is when they start getting negative, the meaning can become a little ambiguous. All right, so technically, if I go from a correlation coefficient from -0.5, whoops, I don't know why I had that extra decimal point there, to -0.7, that correlation coefficient in a mathematical sense is going down because -0.7 is technically smaller than -0.5. And it just becomes confusing using words up and down when you're talking about correlation coefficient. What I would say is instead use the words strengthen and weaken are usually better choices because there's less ambiguity. Like I can go, oh, this correlation coefficient is strengthening in a negative direction, right? And that way there's no ambiguity about using the words like up and down, and like Well, do you mean up because it's stronger, or do you mean like mathematically up, which then means it's actually getting weaker in a negative direction? So again, just when you're talking about these, I would avoid the words up and down because they can just make things very confusing. Strengthen and weaken. And basically, the closer it gets to 1, it's strengthening in a positive direction. The closer it gets to -1, it's strengthening in a negative direction. And as it gets closer to 0, the relationship is weakening. And you can either come into that from the positive side or you can come at that from the negative side. But as you get closer to 0, the relationship is weakening. So again, just be careful with your language when referring to these correlation coefficients because it can get confusing if you start using words like up and down and what you actually mean. All right, so let's look at this next question. Which one shows a stronger relationship? The one on the left or the one on the right? All right, so make your guess, and then I will tell you the answer. All right, so the answer is, this is a trick question. It's the same data. Right? It's just the same data with different scales. And that's part of the reason that we have the correlation coefficient, is that sometimes graphically it can be hard to tell. All right. There's a lot of evidence that people are bad at estimating this just by graphically looking at it. And the correlation coefficient sort of takes that graphical side out of it and just gives it a number that we can apply. So even if you looked at these and thought like, oh, this one's stronger than this one, the correlation coefficients would be the same, and then you wouldn't have to worry about that. There's a great site that is strangely addictive called guessthecorrelation.com, and I would strongly encourage you to go check it out. And it basically just shows you a bunch of different correlation plots and then asks you to guess what they are, and you get points depending on how close you are, and if you're too far away, you like lose a life, and if you lose all 3 lives, the game ends and you get your final score. But I would check it out because it does show that as much as like we think like, oh, correlation, we just look at the picture and have an idea, sometimes the pictures can be deceiving, and what we think is a strong correlation is actually a weak correlation, or what we think is a weak correlation is actually a strong correlation. So again, you just have to be careful looking at graphs because they're not always going to be what you think they are. Now, with that said, here's a few examples just so you can get sort of a frame of reference. All right, this one would be about a correlation of 0. There's not really any direction. This one, we can start to see the general pattern here sloping down to the right. So that's got a correlation of -0.3. Here we have a much stronger pattern going up to the right, so this would be a positive 0.5. It's getting stronger still as we go down here, so this is -0.7. Stronger still, but in a positive direction, so 0.9. And then extremely strong, -0.99. And they're just approaching sort of that linear pattern. But notice on each of these, I didn't say up or down, I said stronger or weaker. So each one of these is getting stronger, even though the numbers are kind of flipping back and forth between positive and negatives. All right. So let's talk about how this number is actually calculated. All right, so our correlation formula is R equals 1 over n minus 1. All right, so n would be your sample size, times the summation. So we're going to be adding up a whole bunch of different things. And what are we adding up? Well, we are adding up x sub I minus x bar over s of x times y sub I, y bar over s sub y. All right, so let's just make sure that we're clear on everything here. R is the correlation. N is your sample size. All right. X sub I is your observation. So that's the part that keeps changing as we go through all the points that are part of your scatter plot. X bar is your mean. And S of X there is your standard deviation. So hopefully this formula looks familiar to you because it is our z-score formula. So another way to think of this is R equals 1 over n minus 1 summation of z sub x times z sub y. Now, when you add a bunch of things up and divide by how many there are, and again, we're not dividing exactly by how many there are because we're dividing by n minus 1, kind of like we do in the standard deviation calculation, what you're effectively doing is calculating an average. So the correlation coefficient is really an average of the product of your z-scores. So you have your xy coordinates, all right, for your scatter plot. Let's just pretend you've got a whole bunch of coordinates, all right? Maybe one is 7, 12, and another one is 10, 18, and another one is 8, 13, and another one is 12, 15. You have a whole bunch of coordinates. All of these get turned into z-scores. Then we take the product and then the final step is to average those products. All right, so that's effectively what's happening here. All right, we are taking a bunch of coordinates that make up our scatter plot. All right, this is what makes up our scatter plot. And then we're turning each of those coordinates into a z-score. All right, so zx, zy, zx, zy, zx, zy, zx, zy. We're multiplying those two things together. So we'll multiply these together, get a number, multiply these, get a number, multiply these together, multiply these together. And then eventually we're going to take an average of all of those products. All right, that's what this formula is actually showing us here. All right, so understanding this formula can help us sort of understand where these values come from and why the correlation coefficient can be positive or negative and so on and so forth. All right, so imagine you have your XY coordinate grid. All right, we know in the coordinate 1, both X and Y are positive. We know over here in coordinate 2, the X is negative and the Y is positive. We know down here they're both negative, and we know over here that the X is positive and the Y is negative. All right, so we know that when things have a positive, we know when the points are moving in a positive direction, we end up with a positive correlation. So points like this would end up with a positive correlation. Now, if we start to think about this as a product of z-scores, we can see why that would be the case. All right, if you consider the points right at the origin, basically where the z-scores are 0, if your points are moving up and to the right, you're going to be having a positive x z-score times a positive y z-score, which is going to give you a positive number because positive times positive is positive. Down here, these are going to be where you have negative z-scores. So if you have a negative times a negative, it still works out to be positive. So you're going to be averaging together positive numbers and positive numbers, which is why we're going to end up with a positive correlation. All right. In contrast, if you had points going down this way, you'd be multiplying a negative XZ score with a positive YZ score. Negative times a positive is going to give you a negative. When they're going down this way, you're averaging together a positive XZ score with a negative YZ score. So again, you're going to have a negative product. And when you're going in this direction, you're going to be averaging together negative values. So that's where the negative correlation is going to come from. Now, if you have points that are all over the place, all right, so if you have points that are all over the place, you're going to end up with positive products here and here. You're going to end up with negative products here and here. So altogether, when you start to average together the positives and the negatives, they're going to cancel each other out. And that's what's going to lead to your correlation of 0, because the positives and negatives are canceling each other out. All right, so by understanding this formula, you can start to see where these values are coming from. All right, when you have a correlation of 0, it's the negative products canceling out the positive products. When you have a positive correlation, it's the positive products overwhelming any negative products that you end up with. And when you have a negative correlation, it's the negative products overwhelming the positive products. So we have a couple of questions here about extreme observations. And it says, what happens to the correlation when we add a point that is an outlier? All right, so what happens if that point is at the center of the data set? So let's pretend we've got our data set here, and there's some X, Y points like this. This is saying, what if your outlier is here? All right, so your outlier is at the center of the cloud, like left to right, but it is an outlier because you've got your cloud here and then the points down here. Versus this one says, what happens if the point is at one of the ends of the data set? All right, so let's look. That would be a situation like, okay, we've got this right here. So in both cases, it might be the same like distance away, but in one case, you're at the end of the data set, and at the one case, you're at the middle of the data set. All right, so this one right here is going to lower the correlation. I can't believe I just said lower. Weaken the correlation. But by a smaller amount. This one's also going to weaken the correlation because it goes against the pattern. But by a larger amount. Now, let's talk about why this is. All right, when you're towards the center of the data set, one of your z-scores is going to be close to 0. All right, so in this case, the way that I drew this plot, my XZ score is going to be close to 0 because it's right towards the middle, where my YZ score is going to be quite a bit negative. All right, so if I'm doing a small X times a large Y, it's only going to be a medium value that's going to affect the average, because remember, the correlation is just the average of z-scores, but it's not going to have as large of an effect because this large y that's the outlier is being counteracted by this small x because that's towards the center of the distribution. Here, with this one, we have a large x times a large y. That's going to give us a really large product that's being put into our average, and that really large product is going to have a more dramatic effect on the correlation. So outliers towards the center of the distribution have a smaller impact because one of these two values ends up being really close to 0. And if this is 30 and this is 0, all right, it ends up being 0. The fact that this is 30 becomes irrelevant. It wouldn't matter whether this was 30 or 50 or 100. If this is 0, it's going to get wiped out either way. Versus down here, if you have a large X z-score and a large Y z-score, the product of those is going to become even larger, which is going to have a more significant impact on the correlation. Now, this same problem can happen when the point follows the pattern of the data. So let's say you have something like this, where you've got a bunch of points down here that maybe the pattern isn't that strong, and then you put one point way out here. All right. This can strengthen the correlation by a large amount. And again, it's because you've got this large X times the large Y. So let's kind of summarize here. First of all, if the point or the outlier goes against the pattern, it's going to weaken the correlation. All right. If you have a point going against the general pattern, it is going to weaken the correlation because it's going against the grain from having mostly positives to like one big negative, or having mostly negatives to one big positive. Now, how much it weakens the correlation depends on its position. If it's towards the center, it's going to weaken it less. If it's towards the edges, it's going to weaken it more. Now, the same thing can happen here when you have a point that follows the pattern. When you have a point that follows the pattern, it's not going to weaken the correlation, it's going to strengthen it. And if it's way out here towards the edge, it could strengthen it by a lot and give a misleading representation. All right, this one point could end up giving you a correlation fairly close to 1 when the rest of the data really doesn't support that. So this one point could give a very misleading value, which again is why it's always important to look at the graph and not just take it based off the numbers. All right, so moving on. I have to give the standard warning that every statistics teacher gives when we talk about correlation. Correlation does not equal causation, right? Just because two things are correlated does not mean that one is causing the other, right? Instead, right here, it says, when we talk about experimentation, which is going to be the next unit, you'll see the only way to control all other influences in a study is through a well-planned experiment. Therefore, even a very strong correlation does not prove that one thing causes another. All right, so an example from recent history. This summer, there was a big news story that said there was a high correlation between people that were going to eat inside at restaurants and those people that eventually tested positive for COVID, right? There was a high correlation. That does not necessarily mean that going to eat at restaurants caused you to test positive for COVID, right? It could just be that those two were correlated, and maybe the type of people that were eating inside at restaurants were doing other behaviors or taking other risks that actually led them to contract COVID, right? It did not imply that eating at restaurants is necessarily the reason they contracted COVID. It could just be that they were correlated and there was some other behavior that was connected to that was actually driving the infections, all right? And that other behavior is a lot of times what we refer to as the lurking variable, all right? So it could be a variable other than X or Y, so other than the two that we're looking at, that affects both variables simultaneously. All right, so it's affecting both of them simultaneously, accounting for the correlation between two variables. All right, so it might be that, going back to our COVID example, that people that were eating inside at restaurants are also people that really like to lick doorknobs. I know it's weird, but I'm sure there are people out there that like to lick doorknobs. Licking doorknobs is probably what actually caused the COVID infections, not going to eat at restaurants. But the fact that people that eat at restaurants also like to lick doorknobs drove the correlation between restaurants and COVID, even though it wasn't actually the restaurants that were causing people to contract COVID. All right. So again, the idea that correlation doesn't necessarily equal causation. All right, let's take a look here. More scatter plots and correlations. So again, I'm going to further drive home the point that it's important to look at graphs. So normally if we were in class, I'd divide the class up and each group would put in one of these into their calculator. But I've already got all three in my calculator here. So stat edit, they're all in the various sections of my calculator. And what we're going to do is we're going to run a regression on each of these and get the correlation. Now, correlation doesn't automatically show up on your calculator. There's usually two ways to get it. You can either go to mode and scroll down, and you want to make sure that stat diagnostics are on. If when you go to mode, you don't see this option, all right, the other way you can get it is you can go to catalog, which is down here on the 0 key, and go second catalog. It'll bring up the catalog. If you then hit the letter D, which is this X to the -1, it'll bring you down to the Ds. And if you scroll down, you can get to diagnostic on and turn it on that way. Either way, you want to have that on, otherwise you won't actually see the correlation. So what I'm going to do is I'm going to go to stat calc. I'm going to go to linear regression. I'm going to put in L1 and L2. And then I'm going to hit enter. Oops. And I can see for this first one, I ended up with an equation of y hat, and we'll get to that later, but right now I'm just going to write it this way, is 0.51x plus 2.96 with a correlation, because again, R is my correlation, of 0.82. All right, now let's go do the next one. Stat calc, linear regression. This time for me, it's in L3 and L4. And this time I'm ending up with a y hat of 0.5x plus 3.00 with a correlation of 0.82. All right, so same correlation and very similar equation. And then let's see, data set 3. I'm going to go to stat calc, lin regression. This is L5 and L6 for me. Calculate that out. And I am getting a y hat of, that's going to round up to 0.50 x plus 3.00 with a correlation of 0.82. All right, so looking at those values, they're all pretty similar, even though all the data sets are different. And all of the correlations worked to be about exactly the same. So it says, from the equations and R values, what can you say about these three data sets? Do you consider the linear regression line a good fit for any of the distributions? So if I'm just looking at this, I would say, sure. They all have strong correlations. All right? And then strong is another way of saying close to 1. All right? So they all have pretty strong correlations. So their linear model is probably a good fit. Now, what happens if we make a scatter plot for all of these? Right? And let's see if we look at the scatter plot. All right, so if I go to stat plot and I do one on L1 and L2, I go to zoom 9. Oops. All right, zoom 9. There's my first one. All right, so my first one is kind of what we're used to seeing. We've got a cloud of points. All right, so I'm just going to sketch this really quickly here. All right, so generally that's the cloud of points. And our regression line would go right through that. And it would be great. All right, no problem. That's kind of what we're trying to do. All right, now let's see if I switch this over to the second one. All right, so I'm going to switch this over to L3 and L4. I'm going to zoom 9. So this time, I can see that my points are actually curved, right? But I ended up with more or less the same regression line. All right, so all have the same correlation, but this one, the regression line, is pretty much going through the cloud of points the way we want it to. This one, it's totally missing the fact that the relationship is curved. Now let's take a look at the last one, because the last one's the strangest yet. All right, so L5, L6. All right, on this one, I have a whole bunch of points that are just vertically lined up here. And then I have one point way out there. And again, the regression line would totally miss out on what's happening. All right, and this is why it's still important to look at your scatter plots and graph your data. All right, if you take a totally numerical approach, you would say, oh, look, all three of these have a pretty high correlation. We're good to go. These must be reliable models that we can use. But when we look at the data, we can see that only one of these is actually capturing what's going on. All right, this one, even though it has a high correlation, totally misses what's going on. This one, even though it has a high correlation, is totally missing what's going on. All right, so in which of these three cases would you actually be willing to use the regression line? Only A. All right, so when we're investigating data, we can't rely only on the correlation. We have to look at the scatter plot. Should have made that line longer. We have to look at the scatter plot as well, because these numbers by themselves can be misleading. They might not actually capture what's happening in the data. So it's important that we look at all of those things together. All right, so take a look at the back here. Final thoughts on correlation, kind of summing things up here. All right. Correlation makes no distinction between explanatory and response variables. Switching which one's the explanatory and which one is the response does not affect the correlation, right? Well, does that make sense? Yeah, it does make sense because correlation is the average of Zx times Zy, and multiplication is commutative, which means the order doesn't matter. So yeah, if I goof up X and Y, it's still going to give me the same correlation. All right. Number 2, correlation coefficient R does not change when we change the units of measurement of X, Y, or both. If you change units, correlation doesn't change. Well, yeah, because z-scores are unitless. All right, we saw this in the last unit that changing units doesn't change the z-score because the z-score kind of eliminates the issue of units. All right, it's just looking at how many standard deviations you are from the mean. All right, the correlation coefficient itself has no unit of measurement, again, because it's based on z-scores. R is a number that approximates the strength of the linear relationship. There are no units involved, right? Again, because it's based on z-scores. So understanding that formula helps explain what we're seeing on this back page here. All right, both variables must be quantitative in order to calculate the correlation, all right? So it's based off a scatter plot. Scatter plots rely on quantitative data, so correlation coefficients also are going to rely on quantitative data. Correlation does not describe curved relationships between the variables, no matter how strong the relationship is. So again, by definition, it only is measuring the strength of a linear relationship. Yeah, we can technically calculate it for a curved relationship, but it's meaningless. All right, we just saw that on the last page. All right, you need to have a linear relationship for this to be valuable. All right. Last but not least, like mean and standard deviation, the correlation is not resistant. R is strongly affected by a few outlying observations. All right. And again, this is what we saw on that earlier page. An outlier in the middle of the data set will weaken the correlation, but an outlier near the edge of the data set could completely change even the direction of the relationship. All right. So outliers near the edge have more impact than outliers towards the middle. And again, that ties back to the fact that we're multiplying these numbers here. And if one of them's towards the middle, one of these could be 0 or close to 0, and it's going to reduce the impact of the other one being large. Versus when it's at the edge, both of these are going to be large, which is going to have an outsized impact on your average. So this is where understanding the formula and understanding where things come from can help you better understand and interpret scatter plots and graphs and see what's happening with the various pieces there. All right. So I hope this was helpful. What we're going to do now is a little activity. All right. This is sort of making up for the fact that you had such a short warm-up. Not making up, but it's just this is why you had such a short warm-up, is so that we could have time for this activity. All right. So the activity is as follows, and it just deals with scatter plots and kind of correlations and what we were just talking about, is I want you to pause the video and guess the age of each of these people. All right. If you don't know who somebody is, it's going to be really hard to make a guess, but make a guess just the same. And then come back and I will tell you what their age is in the year 2020. All right. So I'm hoping you paused the video, made your guesses. Here are their ages. So we've got 74, we've got 59, we've got 46, we've got 30, 66, 44, 65, 74, 34, 53, 42. I'm putting these in the estimate category, but I should have put them in the actual category. It doesn't really matter because presumably you already put your guesses in the right spot. 31, 46, 35, and 45. All right, so let's talk about what the questions actually say here. So how well were you able to estimate the ages of these people? To help answer this question, use your calculator to make a scatter plot with your estimated age on the horizontal axis and your actual age on the vertical axis. All right, so you're going to want to type these into a calculator at this point. What I did is I went over and I've already got them in my calculator here. All right, they're way over here. So I've got the actual values over here. I just made up some guesses since I was the one that looked them up. I couldn't really guess. But I've got some random values over here. So again, to make the scatter plot, I would go to stat plot. I would make sure that it's on. And then you just have to make sure that you've got them in the correct lists. So mine are in lists A and B. Yours are probably just in L1 and L2. I just had everything pre-entered in my calculator. And then I can go to graph. And if you're not seeing anything, you just need to go to Zoom 9 and that'll show it. So yours might not look like this. Yours might look totally different. But if we've got sort of our grid here of X was going to be our guesses and Y was going to be the actuals. All right. And mine, again, looked something like this. But again, I was just kind of making it up. So whatever. So the questions here are, once you've got yours, how would you decide if someone were a good estimator of the ages for this group of people? All right. So what would you be expecting to see in your graph if somebody was a fairly good estimator? All right. Now, remember, you've got your guess and your actual here. So presumably, you'd want them to be kind of following this strong linear relationship, where as the guesses went up, it corresponded to their actual age being higher. Right? What you don't want to see is somebody guessing really high when their actual age is really low, or guessing really low when their actual age is really high. So what would you hope to see? You'd hope to see a strong, positive, linear relationship. All right, so that's using all of those words from our notes from last time. All right, where will the points lie if your estimate was correct? Draw in the line that represents estimates that are 100% accurate. So if you were 100% accurate, your guesses would be directly in line with the actuals. So you'd basically have this line down the center where a guess of 30 corresponds to an actual age of 30, or a guess of 40 corresponds to an actual age of 40, or a guess of 50 corresponds to an actual age of 50. So this would be the correct line, all right, where everything is correct. Now, all right, so that's this one right here. What does it mean if a point is above the line or below the line? All right, so if this is totally correct, what happens when you end up with something that's above the line here, or what happens when you get something below the line here? All right, so when something is below the line, and let's put a point way down here just to make it more obvious, all right? This is saying that you guessed really high, but their actual age was pretty low, right? If you have a point way here, this is saying that you guessed low, but actual, was high. And then this is the reverse, all right? Right here would be you guessed high, when the actual was low. So what does it mean when the point is above the line? All right, it means your guess was too small. And what does it mean when it's below the line? All right, that means your guess was too high. And again, this is just to get you more comfortable with like analyzing one of these scatter plots and thinking about them in a deeper way than just, well, my teacher told me to graph it, so I graph a bunch of XY coordinates and there it is, and I'm done. It's thinking about what these points actually represent in sort of a larger setting. And again, this setting is just guessing ages, but it can be applied to other fields as well. Like you've got this estimate line. What does it mean if this is the line of perfection? What does it mean to be above? What does it mean to be below? And then the last question just says, in general, are you an overestimator or an underestimator? That's going to change based on your specific graph. But how can you tell? You're basically looking at the number of guesses above the line versus the number of guesses below the line. All right. And normally what I have kids do is I actually have them calculate the correlation of these points. And then we see who ended up with the highest correlation or who is kind of like our best overall guesser. So if you want to calculate yours and like brag to your friends about your correlation, you're welcome to do that. Or if you're like, Mr. Vaughn, that's super lame, I'm not going to do that. I wouldn't agree with you, but I think I would understand. All right. So again, I hope this was all helpful. I hope this was all interesting. And have a great day. Bye.